Let's take a look at how to find the derivative of an exponential function. So we're going to start with our definition. Let u be a differentiable function of x. The derivative of e to the x is itself, e to the x. This came from the limit definition of a derivative. We're just not going to go through the derivation. The derivative of e to a function of x, a u, let's say, will be e to that function times the derivative of the function. So it'll be e to the u times the derivative of u. Let's take a look at how this works. So, find the derivative of each function that follows. Number 1, y equals e to the 7x. To find the derivative, pretend that u is equal to 7x. And then this is really just y equals e to the u. And then it follows the second rule in our definition. The derivative will be dy dx is equal to e to the u, which is 7x, times the derivative of 7x, which is 7, or 7e to the 7x. All right, let's take a look at the second one. We have y equals e to the 5 over x squared. First thing I'm going to do is rewrite that. When I look at 5 over x squared, if I wanted to do the derivative of that the way it's written now, I'd have to use the quotient rule, which we all know you want to avoid, if possible. So, this is the same as e to the 5x to the negative 2. And now the derivative of that, dy dx, or y prime if you prefer, is equal to exactly itself, e to the 5x to the negative 2, times the derivative of 5x to the negative 2. So power rule for derivatives says take the exponent, multiply it by 5 to get negative 10, keep the x, subtract 1 from the exponent to get negative 3. So if I clean this up a little bit and try to get rid of those negative exponents, in the top I'm going to have a negative 10, e to the 5 over x squared, put it back the way it was, divided by x cubed. Okay, so those are our first two examples. Example number 3. F of x is equal to e to the x minus 3, all divided by e to the 2x. Let's rewrite the original function. I have e to the x minus 3 times e to the negative 2x. It works the same way as if I had had x squared in the denominator. I could write that up top as x to the negative 2. Same logic, just different bases and exponents. If I distribute, I can add exponents on the e to the x and the e to the negative 2x to get e to the negative x minus 3e to the negative 2x. Okay, now keep in mind this is all still the original function. I haven't done a derivative yet. The derivative of this, f prime of x, is equal to, okay, the derivative of e to the negative x is e to the negative x times the derivative of negative x, which is negative 1. And then I have minus 3. The derivative of e to the negative 2x is e to the negative 2x times the derivative of negative 2x, which is negative 2. And now I just want to go through and clean it up a little bit. So this is going to be negative e to the negative x plus 6e to the negative 2x. Which we can then express as negative 1 over e to the x plus 6 over e to the 2x to get positive exponents back. Okay, two more. Problem number 4. G of x is equal to the natural log of e to the x plus 4 over 1 minus e to the x. So the first thing I'm going to do is split this using the properties of logarithms. So the natural log of a quotient is equal to the natural log of the numerator minus the natural log of the denominator. And now I've made it a lot easier. Now, just a quick reminder, the derivative of ln u is equal to 1 over u times the derivative of u. So we're going to use that to do the derivative of these two different natural logs. So now my derivative, g prime of x, is equal to, let's focus on just the first natural log, 1 over the inside times the derivative of the inside. The derivative of e to the x is e to the x. The derivative of plus 4 is nothing, so I just need the e to the x. Now I have minus the derivative of the second natural log. So that's 1 over what's written inside times the derivative of what's written inside. So the derivative of 1 is 0. Then I have negative derivative of e to the x is e to the x. Again, don't worry about a common denominator here. You can just make sure you condense the fractions down a little bit, and you'll be all set. Be careful here, you have negative in the middle and then a negative at the end, so this really is a plus e to the x over 1 minus e to the x. So you can stop here. And now for our final example. This one has a little bit more to it than the others did. When I look at y equals 3x squared e to the sine 4x, there's a lot going on. But the first thing I notice, there's a product here. So I have to do the product rule. So let's get this started. dy dx equals the derivative of 1, so the derivative of 3x squared is 6x, times the other, e to the sine 4x, plus, now to do the opposite, put the 3x squared back, and now I have to multiply by the derivative of e to the sine 4x. So the derivative of e to the something is exactly itself. But now I have to multiply by the derivative of sine 4x. Well, the derivative of sine is cosine. But then since it's cosine of 4x and not cosine of x, I also have to multiply by 4. So there's a lot going on in that part of the problem. So our derivative is 6x e to the sine 4x plus. I have 3x squared, and then I have a 4 at the end that are being multiplied together, so I have 12x squared. I'm going to write the e to the sine 4x next, and then the cosine 4x after it. If you wrote it in a different order, that would be fine too. It doesn't really matter the order that you put it in. If you wanted to, you could factor out a GCF, but it's not really going to help to make things look any easier, so you can leave it like this. Alright, that's it.